So I've got a rocket here, and this rocket is going to launch a projectile, maybe it's a rock of some kind, with the velocity of 10 meters per second, and the direction of that velocity is going to be 30 degrees upwards from the horizontal, or the angle between the direction of the launch and the horizontal is 30 degrees. And what we want to figure out in this video is how far does the rock travel? We want to figure out how far does it travel? Does it travel? And to simplify this problem, what we're going to do is we're going to break down this velocity vector into its vertical and horizontal components. We're going to use a vertical component, so let me just draw it visually. So this velocity vector can be broken down into its vertical and its horizontal components. So we're going to get some vertical component, some amount of velocity in the upwards direction, and we can use that to figure out how long will this rock stay in the air. Because it doesn't matter what its horizontal component is, its vertical component is going to determine how quickly it decelerates due to gravity and then reaccelerates, and essentially how long it's going to be in the air. And once we figure out how long it's in the air, we can multiply it by the horizontal component of the velocity, and that will tell us how far it travels. And once again, the assumption that we're making in this video is that air resistance is negligible. Obviously, if there was significant air resistance, this horizontal velocity would not stay constant while it's traveling through the air. But we're going to assume that it does not change, that it is negligible. We could assume that we're doing this experiment on the moon if we want to view it in purer terms. But let's solve the problem. So the first thing we want to do is we want to break down this velocity vector. We want to break down this velocity vector that has a magnitude of 10 meters per second and has an angle of 30 degrees with the horizontal. We want to break it down into its x and y components, or its horizontal and vertical components. So that's its horizontal. Let me draw a little bit better. That's its horizontal component, and then its vertical component looks like this. This is its vertical component. So let's do the vertical component first. So how do we figure out the vertical component given that we know the hypotenuse of this right triangle and we know this angle right over here? And the angle and the side, this vertical component, or the length of that vertical component, or the magnitude of it, is opposite the angle. So we want to figure out the opposite. We have the hypotenuse. So once again, we write down SOHCAHTOA. Sine is opposite over hypotenuse. So we know that the sine of 30 degrees, is going to be equal to the magnitude of our vertical component. So this is the magnitude of velocity. I'll say velocity in the y direction. That's the vertical direction. Y is the upwards direction. Is equal to the magnitude of our velocity in the y direction divided by the magnitude of the hypotenuse, or the magnitude of our original vector, divided by 10 meters per second. 10 meters per second. And then to solve for this quantity right over here, we multiply both sides by 10, and you get 10 sine of 30. 10 sine of 30 degrees. 10 sine of 30 degrees is going to be equal to the magnitude of our vertical component. And so what is the sine of 30 degrees? And this, you might have memorized this from your basic trigonometry class. You could get the calculator out if you want, but sine of 30 degrees is pretty straightforward. It is 1/2. So sine of 30 degrees, use a calculator if you don't remember that, or you remember it now. So sine of 30 degrees is 1/2. And so 10 times 1/2 is going to be 5. So, and I forgot the units there. So it's 5 meters per second is equal to the magnitude of our vertical component. Let me get that in the right color. It's equal to the magnitude of our vertical component. So what does that do? Well, this projectile, because its vertical component is 5 meters per second, it will stay in the air the same amount of time as anything that has a vertical component of 5 meters per second. If you threw a rock or projectile straight up at a velocity of 5 meters per second, that rock or projectile will stay up in the air as long as this one here, because they have the same vertical component. So let's think about how long it will stay in the air. Since we're dealing with the situation where we're starting at the ground and we're also finishing at the same elevation, and we're assuming that air resistance is negligible, we can do a little bit of a simplification here. Although I'll do another version where we do it in the more complicated, but I guess the way that applies to more situations. We could say, well, what is our change in velocity here? So if we think about just the vertical velocity, our initial velocity, let me write it this way. Our initial velocity, and we're talking, let me label all of this. So we're talking only in the vertical. Let me do all of the vertical stuff. Let me do it in blue. So vertical. We're dealing with the vertical here. So our initial velocity in the vertical direction, is going to be 5 meters per second. Is going to be 5 meters per second. And we're going to use a convention that up is positive and that down is negative. And now what is going to be our final velocity? We're going to be going up, and we're going to be decelerated by gravity. We're going to be stationary at some point, and then we're going to start accelerating back down. And if we assume that air resistance is negligible, when we get back to ground level, we will have the same magnitude of velocity, but we'll be going in the opposite direction. So our final velocity, remember, we're just talking about the vertical component right now. We haven't even thought about the horizontal. We're just trying to figure out how long does this thing stay in the air. So its final velocity is going to be -5 meters per second. If this is the initial velocity, the final velocity is going to be looking like that. Same magnitude, just in the opposite direction. So what's our change in velocity in the vertical direction? Change in velocity in the vertical direction, or in the y direction, is going to be our final velocity, -5 meters per second, minus our initial velocity, -5 meters per second, which is equal to -10 meters per second. So how do we use this information to figure out how long it's in the air? Well, we know that our change in our vertical velocity is going to be the same thing, or it's equal to our acceleration in the vertical direction times the change in time, times the amount of time that passes by. What's our acceleration in the vertical direction? Well, it's the acceleration due to gravity, or the acceleration that the force of gravity has on an object in free fall. And so this right here is going to be -9.8 meters per second squared. So this quantity over here is -10 meters per second. We figure that out. That's going to be the change in velocity. -10 meters per second is going to be equal to -9.8 meters per second squared times our change in time. So to figure out the total amount of time that we are in the air, we just divide both sides by -9.8 meters per second squared. So we get, let's just do that. I want to do that in that same color. So I do it in, that's not, well, that's close enough. So we get -9.8 meters per second squared, -9.8 meters per second squared. That cancels out. And I get my change in time. And I'll just get the calculator. I have a negative divided by a negative, so that's a positive, which is good because we want to go in positive time. We assume that the elapsed time is a positive one. And so what do we get if I get my calculator out? I have, this is the same thing as positive 10 divided by 9.8. 10 divided by 9.8 gives me 1.02. I'll just round to 2 digits right over there. So that gives me 1.02 seconds. So our change in time, so this right over here is 1.02. So our change in time, our delta t, well, I'm using lowercase now, but I could make this all lowercase, is equal to 1.02 seconds. Now, how do we use this information to figure out how far this thing travels? Well, if we assume that it maintains its horizontal component of its velocity the whole time, we can just multiply that times our change in time, and we'll get the total displacement in the horizontal direction. So to do that, we need to figure out this horizontal component, which we didn't do yet. So this is the component of our velocity in the x direction, or the horizontal direction. Once again, we break out a little bit of trigonometry. This side is adjacent to the angle. So the adjacent over hypotenuse is the cosine of the angle. Cosine of an angle is adjacent over hypotenuse. So we get cosine cosine of 30 degrees, I just want to make sure I color code it right. Cosine of 30 degrees is equal to the adjacent side, which is the magnitude of our horizontal component, is equal to the adjacent side over the hypotenuse, over 10 meters per second. Multiply both sides by 10 meters per second. You get the magnitude of our adjacent side. The color transitioning is difficult. The magnitude of our adjacent side is equal to 10 meters per second, times the cosine of 30 degrees. And you might not remember the cosine of 30 degrees. You could use a calculator for this. Or you can just, if you do remember it, you know that it's the square root of 3 over 2. Square root of 3 over 2. So to figure out the actual component, I'll still have to get a calculator out if I want. Well, I don't have to do it just yet, because I have 10 times the square root of 3 over 2, which is going to be 10 divided by 2 is 5. So it's going to be 5 times the square root of 3 meters per second. So if I want to figure out the entire horizontal displacement, so let's think about it this way. The horizontal displacement, that's what we're trying to figure out. The horizontal displacement, S for displacement, is going to be equal to the average velocity in the x direction, or in the horizontal direction. And that's just going to be this 5 square roots of 3 meters per second, because it doesn't change. So it's going to be 5, I'll do that same color. It's going to be the 5 square roots of 3 meters per second times the change in time, times how long it is in the air. And we figured that out. It's 1.02 seconds times 1.02 seconds. The seconds cancel out with seconds, and we'll get an answer in meters. And now we just get our calculator out to figure it out. So we have 5 times the square root of 3 times 1.02 gives us 8.83 meters, just to round it. So this is going to be equal to, this is going to be 8.83, is that what the number I got? 8.83 meters. And we're done. In the next video, I'm going to try to, I'll show you another way of solving for this delta t, to show you really that there's multiple ways to solve this. It's a little bit more complicated, but it's also a little bit more powerful if we don't start and end at the same elevation.